Okay, so here's what I intend to be a very quick video to go over some assorted questions on polar coordinates and parametric equations. It will be quick. This is not a video to learn this from if you don't know anything about it. The finer details of all these problems would have been covered in other videos or somewhere else, okay? But I just wanted to give you some questions and some answers and show you a little bit of everything in one video. So first one, can you convert a point that's in polar coordinates to rectangular coordinates? Okay, so 2 and 5 pi over 4, so 5 pi over 4 is to 25 degrees. It's about like that. It's down in quadrant 3, and the formula for converting from polar to rectangular is fairly straightforward. The x-coordinate is going to be r cosine theta, the y-coordinate r sine theta. Okay, so it's like saying that point could be seen as left root 2 and down root 2, x and y, left and right and up and down. That's what rectangular coordinates are. Let's look at another one, converting to rectangular coordinates. So this polar coordinate was given as root 2 for r and 2.35 for theta, and that's not 2.35 degrees. It is an angle, you know, but I'd have to see that as a radian angle. 2.35 radians is about 134.6 degrees. That would mean this point is over here in quadrant 2. Rotate about 134 degrees, go out a radial distance of root 2. That's where your point is. We can use the same formula as in that first problem, r cosine theta, r sine theta. Those are the rectangular coordinates. It turns out you get that point by going left 0.993 and then up 1.006. Left and up, x and y. Okay? All right. So let's look at another one, converting to rectangular coordinates. So this time r and theta is given with r to be negative. Theta 0.55 radians. That turned out to be about 31.5 degrees. Okay, 0.55, that's an angle. It's because there's no units given, but we know it's in polar coordinates, so we know it's an angle. We know it's radians then. That's the conclusion that we can reach. This point, well, okay, so I'd have to rotate about 31 degrees, and then since r is negative, I have to go that way, a distance of about 3, okay? It'd put me down here in quadrant 3. Now, that's where it is. Nonetheless, I can convert that to rectangular coordinates the same way. R cosine theta, x-coordinate, r sine theta, y-coordinate. You can get there by going left about 2.5 and down about 1.5. Left and down, that would definitely take you to quadrant 3. Okay? All right. So now, because polar coordinates are such that lots of different combinations of angles, positive and negatives, and radial coordinates are positive and negative can get you the same point. We might see a question where we give 2 sets of polar coordinates for one rectangular coordinate. So take the rectangular coordinate negative 3 and 4. Left 3, up 4. So here's how we can do that. Here's how we can convert from rectangular to polar. First of all, r is pretty easy. R equals root x squared plus y squared. So that's going to be root 25 or 5. The radial coordinate's 5. So like from here to there, that's 5. To find the angular coordinate, I'll find this reference angle in that triangle. So you see that triangle right there? Tangent A is 4/3. A is inverse tangent 4/3, about 0.927 radians. That's how big that angle is. Now, it's said to give 2 sets of polar coordinates, with theta being between 0 and 2 pi. So we could do like this. We could say, look, if that angle in this triangle is about 0.927 radians, this angular coordinate for the polar coordinates is going to be pi minus angle A. Pi minus 0.927. That's about 2.214 radians. Okay. So one answer, r 5 theta 2.24 radians. Is there another way? It said give 2 sets. Is there another way I can do it? Well, what if I rotated like that? Okay, or what if I rotated around here like that? Since it said to give two coordinates with theta between 0 and 2 pi, I'll take 2 pi minus this angle A right here, okay? 2 pi minus angle A. That will be this angle here in quadrant 4, 5.356 radians. So if you dial in this angle right out there, quadrant 4, 5.356 radians, R would need to be negative. So R is negative 5 in that case. So there's two coordinates, two different angles, each between 0 and 2 pi. All right? One in quadrant 2, the other in quadrant 4. All based off of finding that initial angle in that triangle. Okay, so that's question 4. Let's look at question 5. So this one is same style as the last one. Find two sets of polar coordinates for this point in rectangular coordinates. So remember, I can find R is going to be the square root of x squared plus y squared. So that's going to be root 10 in my case. And then I need to know this angle in that triangle. That will be the angular coordinate in my polar coordinates. I can find that with tangent. It turns out it's about 1.249 radians. So one answer would be root 10 for R, 1.249 radians for theta. It said give 2 though. All right, what's another way you can get there? Suppose you rotate it over here in quadrant 3, okay? And then R was negative. That would get you to that same point. What's this angle in quadrant 3? Pi plus theta. That'll be this angle out in that direction in quadrant 3. That's 4.391 radians. If that then is your angle, we need to adjust R to be negative. Okay, so there I got then one angle in quadrant 1, one in quadrant 3 with R negative. Okay, all right, next question, convert to polar form. I believe this one would probably say something like convert to polar form and then graph it or something like that. So say you had this equation, you convert to polar form. What's polar form? Polar form means it's got R and theta. That's what polar coordinates are. Rectangular coordinates are x and y. So we can do that one this way. Some conversions for us to use, converting one way to the other, are that x squared plus y squared is r squared, okay? And that x is r cosine theta. And I said I'd make the video quick. I just want this to be a quick list of assorted problems. So I don't discuss the conversions, but those are the conversions that we use. So we'll get r squared minus 3 times p. P is, whoa, what's p? I didn't talk about that. P is some unspecified constant. It's not given, but it's a constant. So r squared minus 3 times p times r times cosine theta. So there, that's definitely a step in the right direction. X and y are gone. Now we have r and theta. I can move this term to the right, and I can divide out a factor of r. I'll get this. R is 3p cosine theta. Okay? All right, what is this? Well, if we get familiarized with polar coordinates and the types of equations that we see in polar coordinates, this is a circle. It has a diameter out here at 3p. Okay? If you let theta be 0, you'll get r to be 3p. That's where this point is. But it's a circle with its center on the x-axis like that. It has a radius of 3p over 2. Center at 3p over 2 and 0. And I should say those are the x and y coordinates. If we're going to use polar and rectangular coordinates, we have to say which is which. That's a polar coordinate for this point, though. All right? Okay. So let's look at 7. Give the polar equation for y is equal to 4. Okay, so polar equation, again, that would involve r and theta. Before I do that, I'll make note that, well, this is a horizontal line that goes through the rectangular point 0 for x, 4 for y. Okay, how would we convert that? Well, there's one very direct conversion that we can use. In polar coordinates, converting to rectangular, r sine theta is y. So this says r sine theta is 4. We can divide both sides by sine theta. It says r is 4 cosecant theta. So then now you can make this association. In polar coordinates, r is 4 cosecant theta is a horizontal line through this point. R and theta, 4 and pi over 2. All right? Okay. So question 8, give the rectangular equation for r is 3 sine theta. Okay, so that would involve converting it in terms of x and y. Now, my conversion equations are that x squared plus y squared is r squared. X is r cosine theta. Y is r sine theta. Those are my conversions. So I'll take this, I'll multiply both sides by r so that I could use my conversions. I'll get r squared on the left, 3r sine theta on the right. Both of those directly convert. That's x squared plus y squared. R sine theta is y, so that's 3y. Now, I would like to get this in a form where I can recognize what it is. The question would probably say something like, give the rectangular equation in sketch or identify the graph. So I will complete the square on this to get it in the form that's the standard form of a circle, okay? So this is called completing the square, and I'll end up with this, and then I could recognize that as a circle that has a center, 0 and 3/2, where that's rectangular coordinates, and a radius of 3/2, so it's a circle like that. So yeah, r is 3 sine theta. That's going to be a circle with its center on the y-axis, all right? Because I can associate it with this, the known equation of that sort of circle. All right, so that's 8. Let's look at 9. Give the rectangular equation for theta is equal to pi over 6. It's implied there that r can be anything. In polar coordinates, there's such a thing as r and there's such a thing as theta. If you don't mention r, that must mean r can be anything, no restrictions. So where are all the points where the angular coordinate's 30 degrees and r's anything you want? All along this line at a 30-degree orientation to the positive x-axis, okay? So I want the rectangular equation for that line. Well, so what's that? Y equals mx plus b. That's the rectangular equation for a line. So here's the way I do it. This is not the only way to do it, but I say, well, there's a point on this line that has a y-coordinate of 1, and I'll find the x-coordinate of it. I'll say tangent of 30 is 1 over x. I'll identify that x-coordinate to be √3, okay? And so the slope of this line is 1 over √3. So you could say, you know, the slope, it goes through the origin, y equals 1 over √3x. If you rationalize it, you could say √3 over 3x. But I just, through the angle, identify the slope of the line. And from there, I know the form that the equation should take. Okay? All right. So question 10. If you're given a polar equation, can you find the slope at various points on it? Okay? So, all right, there's my polar equation. The slope formula, that's given in another video, or it's something that you can look up right now if you wanted to, but it's always a mess. All right, there it is, though, for this one. There's my slope formula. With a little reducing, I can't do much to simplify it, but I'll get this, okay? And that tells you the slope at any point you want. It just needs an input of theta. So if I take the angular coordinate of a point, and here, this will tell me the slope on the polar graph at that point, okay? So you give me a point where, you know, theta is 3 pi over 2 or pi over 6. I just do the math from there. That's why a question like this will be given sequentially. We got to do this part first in order to calculate the slope at individual points. Okay? All right. 11. So calculate the area inside 2 petals of this. Well, I guess how you graph this is up to you. But if I was going to do this on paper, or if I was going to prove I really understood how the graph is made, in other videos I've done, I've suggested drawing the rectangular graph and then converting that to polar coordinates. So here's the rectangular graph for sine 3 theta. It has a period of 2 pi over 3. And I compress the sine wave within that period. There it is. And I see that r from 0 to pi over 6 increases to a maximum of 4 at pi over 6, but then from pi over 6 to pi over 3, r closes back into 0. So this here on the rectangular graph creates a loop on the polar graph. All right? So there's a loop or a pedal or whatever you want to call it. There's more. I mean, if I keep going, there's more of them than that, but I just needed to see one of them. Okay? So, okay, the bounds for that pedal, angle-wise, are 0 to pi over 3. Okay? So, this integral, the definite integral 0 to pi over 3, 1/2 r squared d theta, that will get me the area of one pedal. And if you ask me for the area of two pedals, then I'll just double that to get the area of two pedals. Okay? From there, it takes some algebra. It takes using a trig identity. It takes using U substitution. Okay, but remember I said the video would be quick. Just an overview. You do all that, you'll get 8 pi over 3. All right. So let's look at 12. Somewhat similar question about area calculation. It says calculate the area inside r is 2 cosine theta, but outside r is 1. So here's r is 2 cosine theta, polar coordinates. It's a circle that has a diameter of 2. This point right here is radially a distance of 2 outward. So this circle has a radius of 1. It has a diameter of 2. R is equal to 1 just is a circle of radius 1, center at the origin. So these circles are the same size. One has center at the origin, the other has a center here on the x-axis at 1. That's what they look like together. They intersect each other at an angular coordinate of 60 degrees or pi over 3. Okay? If you set these equal to each other and you solve for the angle, it would be 60 degrees. All right. So here's how we can get the area that's outside of this one but inside of that one that I've shaded here. We'll take the curve that's radially further away, 2 cosine theta, and square it, minus the curve that's radially closer, which is 1, right? So this is the outer curve squared minus the inner curve squared. And I say outer and inner in a radial fashion. So 1/2 outer radius minus inner radius squared. That's what you're looking at there. Okay, bounds 0 to pi over 3. 0 to pi over 3. 0 to pi over 3 would get me like this here. So I just decided to set it up like that and double it to get the whole thing. All right? Okay, now again, from this point, this is like that last problem I was showing you, where I need a certain trig identity to reduce this integral, and then I use U substitution. Okay, I'll get pi over 3 plus root 3 over 2 if I do that. All right, 13, give the rectangular equation, otherwise known as the path, for x is 2t minus 3 and y is 3t plus 1. Well, with these being algebraic, there's no sine and cosine or anything like that. All we do is solve one for t and put into the other. That will eliminate t. The path gives no information about t, because you could think of parametric equations as giving information about time and place. T is time, x and y is place. So if we do that, we'll get y is 3 over 2x plus 11 over 2 as a linear path. If you were to take these and plot the position at various times, like say you put t as 0, you'd find yourself at this point. Take a later time, take t is equal to 1, you'll find yourself at that point. You're moving along that linear path in this direction. So in parametric equations, we usually put arrows on the graph to indicate the direction that the motion is happening. Okay? All right, so there's 13. 14. Can you give the rectangular equation, otherwise known as the path, for x is 4 sine 2 theta and y is 5 cosine 2 theta? That's not algebraic, so we'll use a trig identity for this one. If I isolate the sine and the cosine, I'll get x over 4 is sine 2 theta, y over 5 is cosine 2 theta. If I square these, they'll have to add to 1. Sine squared 2 theta plus cosine squared 2 theta is 1, so therefore x squared over 16 plus y squared over 25 is 1. This is the equation of an ellipse, okay? All right, so we get our ellipse. it hits the x-axis at 4 and -4 and the y-axis at 5 and -5. This is motion on an elliptical path, but which way, clockwise or counterclockwise? I just plotted positions at a few different times. When theta is 0, you'll find yourself by these equations at 0 for x, 5 for y. And when theta is pi over 4, for example, these equations will put you at 4 for x, 0 for y. So that's motion that's clockwise. All right. So there's the equation, the path, and the graph with the direction. Okay. 15. Give parametric equations for these conditions. The rectangular equation, or the path, is the line y is 4x minus 6. And we insist that you be at the point 3 for x, 6 for y at the time t is equal to 0. All right. So there are many ways you can do this one. I'll show you one way though, okay? So let's see, here's my line, okay? 4x minus 6, that's the path. It has a slope of 4. So it absolutely must be that you're at the point 3 for x, 6 for y when t is 0, okay? So you could say in your answer, x is 3 plus something and y is 6 plus something. That will put you at 3 and 6 when t is 0, because when t is 0, all that's gone. Now, notice on this line, it has a slope of 4. That means on the line, you have to go up 4 over 1. So x and y are individually left and right for x, up and down for y. So I want to start at 3 and go right 1. 3 plus 1t. That will do it. And for y, I want to start at 6 and I want to go up 4. 6 plus 4t. So start at 3, 1 to the right, start at 6, up 4. Okay? So if you can figure out where you want to be when t is equal to 0, translate the slope of the line into left or right, up and down. You can build the parametric equations that way. Okay? All right. Sketch the graph of this. X is 3 theta minus sine theta, and y is 3, 1 minus cosine theta. So I included this one, but then when I got to this point, I thought, well, I did a whole video about a cycloid already, and then so I started to have second thoughts about doing it right here. So I'll just say for that question, it's better just to look at the video I made on the cycloid, okay, rather than reproduce it here, because that's all I would be doing anyway. Okay, so all right, that's an exception to what I'm doing. I'm just going to skip that one. Let's look at 17. Okay, suppose we have projectile motion as something is launched at some initial speed with some initial launch angle to the horizontal at some initial height. So like we launched this projectile and, you know, at a certain angle theta to the horizontal direction and a certain speed right off the bat and at a certain height above the ground. That's what all that is. Okay? In general, this is how that information factors into the equation. The angle is incorporated like that, secant and tangent. The initial speed is incorporated down here, v naught squared. And the height that it's launched from is incorporated here. Okay, so in general, that's how parametric equations, or that's how the information about projectile motion factors into the equation. Now, suppose I tell you for this problem, the actual equation for that parabolic path is y is negative 0.008x squared plus x plus 7. Could you work backwards and figure out the initial speed and the launch angle and the height? Okay, so here's how we do that. This is just supposed to be that. That's the only thing to realize about it. So right off the bat, h has to be 7. Okay, what else? Well, this has to be 1. Right? If these are supposed to match and be equivalent to each other, tangent theta, this coefficient of x, needs to be 1 if it's going to be like this. If tangent theta is 1, theta is 45 degrees. If you want it in radians, 0.79 radians. Okay. All right, what about v naught? What about the initial speed? Well, okay, see this number, 16, negative 16, secant theta squared over V naught squared. That needs to be negative 0.008, just for these to match. So I set that up knowing that I already found the angle to be 45 degrees, okay? And I solved this equation for V naught, and it turns out to be 63.25. So yes, by that I can work out the launch height, the launch angle, and the launch speed, okay? Now say that I know that, then I can find out the maximum height the projectile reaches. That's the vertex of this parabola given by the equation negative 0.008 x squared plus x plus 7. Okay, all right, there's the y-coordinate of the vertex. And then the range, it's asking me for where does the projectile land. That's the x-intercept of this quadratic equation, which we solve by the quadratic formula. Okay, and I'll get 131.65 feet. All right, so that's 17. 18, calculate the slope of this curve at each point and give the equation of the tangent line. So when a curve's given in parametric form, x is t squared minus 4, y is t squared minus 2t, I can find the slope of that curve through this, dy over dt divided by dx over dt. With those, that ends up being 2t minus 2 over 2t, okay? Now, all right, so I've got the thing that tells me the slope. Now, suppose the question goes like this. At the point where x and y are both 0, what's the equation of the tangent line? Now, this demands that you know t. It doesn't demand that you know x and y. So to find the value of t that is corresponding to this point, then I need to do something like this. I'd say, okay, you want x to be 0. So we'll put 0 for x, we'll solve for t, okay? And then we'll get two solutions. We'll get t is 2 or negative 2. But negative 2 through that doesn't give you y to also be 0. 2 does, okay? So 2 gives you x and y to both be 0. So t is equal to 2. All right, so I put that in to this. I'll get 1/2 for the slope. And so my partial answer is the equation of the tangent line is y is equal to 1/2 x plus b. B's the y-intercept. But the origin is on that line. So that means b is equal to 0. Okay, for this one, x and y is negative 3 and negative 1. Now, just like up here, we can take the x's and y's, all right, and solve for the value of t that will obtain them, and that's 1 in this case, all right? In my slope formula, it ends up being 0. That's horizontal, so my answer here is I want a horizontal line that passes through that point. That's going to be y is equal to negative 1. All right, last one, x and y is negative 3 and 3. The value of t for that one is negative 1. The slope is 2. Partial answer, y is 2x plus b. Okay, but given that I know this point is on that line, I can put 3 for y, negative 3 for x. I'll solve b to be 9. Y is 2x plus 9. Okay, 3 points, 3 slopes, 3 tangent lines. So let's look at 19. Calculate the arc length of this parametric curve from t to be 1 and 3. For that, there's a fairly straightforward integration formula. There's your lower value of t, your upper value of t, root x prime squared plus y prime squared. Take the derivative of those, square them, add them together, take the square root. Okay, derivatives of these are 2 and 5. You'll get root 29, t for the antiderivative, 4 root 29, once calculated, if rounded, 21.5. And then one last problem, surface area problem. Say we take this, okay, and we rotate it around the x and the y axis. What's the surface area of this shape that you get? Well, so this ends up being like just, I said I wasn't going to go super in depth because I've already done it. But if like those are a line, and if you take a line and you rotate it around, then you get a cone, okay? So the context of this problem then is like saying, what is the surface area of the cone generated by revolving that line about either the x or the y axis? Okay, so I gave the formula for each one. About the x-axis, if you rotate that way, the surface area of the resultant shape is going to be 2 pi y root x prime squared plus y prime squared. Okay? All right, 2 pi y. Y is what? 5t. So we'll get this, and that. Okay? All right, about the y-axis, if you rotate this way, okay, you get a cone like that. Slightly different shape, different dimensions, okay? The formula is going to be, again, bounds for t, it says 0 to 3 for this. 2 pi x root x prime squared plus y prime squared. So 6 pi t root 34, this, and then that. Okay, so that's a little bit of everything for what is normally the last test, Calculus 2. In other words, polar coordinates and parametric equations.